So capacitors in series is what I asked you to deal with. And hopefully you were successful. So the idea was to take a look at a simple system like this. And right now you don't understand why we're doing this. You're going to, I hope by the end of the class period today. I had something like this, and I wanted you to come up with a relationship for what it would mean to produce an equivalent circuit. And an equivalent circuit is one in which we have one resistor replacing a system of resistors. I'm sorry, I said resistors. One capacitor replacing a system of capacitors. And we're trying to reduce the system down, and I asked you to prove that 1 over the equivalence is equal to the sum of the inverses, basically. And truthfully, you can have any number of these in series, and you'd find the same response. Now, is there anybody who needs evidence of this proof because they didn't do it themselves? I won't say I'm happy to do it, but I will do it. I'll remind you that we started with that yesterday, and I had recommended that you sub in our accepted expression for the potential difference across the capacitor. That gives us a Q1 over C1 minus Q2 over C2 here. Now, the idea of it being an equivalent capacitor is going to be that it too would obey some similar function, right? This is the result of using Kirchhoff's law on our equivalent circuit. Now, if I solve this for V, for the same potential difference, for the same battery, this and this must be equal. So we can set them equal to each other. And on the surface, that's, no big deal. It doesn't really solve anything until you realize something else we talked about yesterday, and that is that when we're in series, the charge on the capacitors has to be the same due to conservation of charge. And I think some of you don't really understand that, but just think, real quickly, if I pluck one positive charge from the bottom plate of that capacitor and place it on the top plate of that capacitor, this isolated part in the middle is going to experience the pressure to move a charge, right? The top plate up there is now positively charged. It's going to push away some positive charge until things equalize. That is going to be equalized when the bottom plate has that one negative charge now, gone. I'm sorry, one positive charge gone, and there's a negative charge. Well, that positive charge had to go someplace, right? If we had uneven charges, then we'd have an electric field, and an electric field would push on the charges until they evened out, which is why the charge has to be the same on all the capacitors in series. So with that, I hope you realize that that makes these the same. But if it's equivalent, then it has to be the same amount of charge that would be in the equivalent circuit. So if I divide by this value, which is we know to be non-zero, then I get this. And moreover, I would get the same thing if I added more capacitors in series. All good? All right, so here's what I want you to do. I want us to experiment with this a little bit, and we need to do some numerical practice. So I want you to imagine to develop an expression for series capacitors. This circuit, as it was, I want to talk about a process we're going to start to learn about called stepwise reduction. Although Kirchhoff's laws is a way to solve circuits, it is the hardest way to solve circuits. Kirchhoff's laws gave us some rules, and we could use those rules for what we're about to do. But imagine I have a 6-volt battery, and I have a 3 farad and 6 farad capacitor. These are outlandish numbers. Capacitors aren't this big unless they're the size of like a 32-gallon trash can. So, which I used to have a 5 farad capacitor in this one classroom I used to teach in. That's like fatal. It's terrible. I would charge it up a little bit. It was about the size of that, but it was shorter, about that big around. I'd leave it on my desk in my college room to wait and see if somebody would just kind of rest their arms casually on it. Because if they touch the terminals, it's basically just it will zap you. So I wouldn't charge it very much, just enough to have plausible deniability. But when a person goes, "What the heck was that?" I'm like, "I don't know. Something happened. What is this thing?" I don't know. It looks like a trash can to me. No fun times. So, the idea that I want you to get is that reducing a circuit is a means of trying to figure out how charges and how your circuit behaves under stress or under load. This is a pretty simple circuit, and we can analyze it using Kirchhoff's laws, but like I said, that's kind of the hardest way to do it. There are some easier ways to do it, and one of them is called stepwise reduction. Stepwise reduction uses the cases that we've been talking about setting up an equivalent circuit, and it uses the concept of reducing your circuit into something simpler in steps. Now, this one can be reduced in one step, so it's, when I say stepwise reduction, this one doesn't really make sense, but eventually we're going to have stuff like, this, where we have multiple capacitors in some kind of complex kind of thing. And even now, drawing this, it's ridiculous. There's no reason to do this. This is an exercise in learning how to reduce circuits. So we'll start with stuff that's simple, and we'll learn some complex techniques, but the idea for us is just to learn this process. These are not particularly functional circuits. I mean, they don't really do anything. We're just learning about the properties of circuits right now. We'll get to some functional circuits later. So in the process of stepwise reduction, you use the formulas for parallel and series circuits. We've only developed one of those, and that was the one for series. But we use that to reduce your circuit. So what that means is I want to find the equivalent capacitance using, I keep saying resistance, but I want to find the equivalent capacitance using the relationship that we just developed for capacitors that are in series. We have 2 in series, so to find the equivalent capacitance, it's just going to be 1/3 plus 1/6, which, be careful here, because you find out that this is 1/2 when you do the mathy math, but that's not the answer. That's the inverse. So to get the answer, you have to invert to find that the actual equivalent capacitance is 2 farads. Now, there is stuff here that you should see that I think is obvious, but it isn't always. Capacitors in series reduce the overall capacitance. Let's see. And I hope that that's not like unobvious. When we talked about capacitors, parallel plate capacitors especially, their design is based on surface area and separation distance. When you place capacitors in series, you're actually increasing the total separation distance. Right? It's spread across 2 capacitors, but that's what's really happening. So the overall capacitance in your circuit goes down because you've increased the separation distance. Does that make sense? So although this is the way in which it's reduced, it's important to note that that's really kind of what's happening. Now, yeah. The area doesn't really increase in this one the way you think it does, because it's not like the charge can spread out over more area. In this case, the charge is still concentrated in the same line. We're fixed with the amount of charge we can pull from this plate and this plate. Those charges aren't spreading out over a greater area. Does that make sense? And that's why. That's why we wouldn't say that the area is greater. Now, I think you can probably imagine, because in a minute we're going to do this. Something that has that look about it. where now I think we could say with the charge can spread out over more area, this is probably going to increase total capacitance. So do you see kind of the difference there? All right, so that means our equivalent circuit has a 6-volt potential difference and a 2 farad capacitor. All right, now you know things, so we're going to use some of the things that you know. We know that voltage equals charge over capacitance, which means that charge equals voltage times capacitance. Well, we can figure out the charge that must be on this capacitor because we can manipulate this function, and we now have the capacitance for the total circuit, and we have the voltage that's been applied to this circuit. This tells me that we must have 12 coulombs of charge separated and placed on the plates of that capacitor. Again, ridiculously high numbers. We're just doing this because the math works out easy. Now, this is the process of solving a circuit. We're doing stepwise reduction. Our first step is to reduce our circuit down in steps. It only took one step to do that, but that's our reduction. When we get our reduced circuit, we apply the rules of charge, capacitance, and voltage to figure out how much charge is on each capacitor and what the potential difference is across each capacitor. That's one of the things I said we'd have to be able to do, is find the potential difference and the charge across each capacitor in the circuit. Now, there's only one capacitor in the equivalent one, which makes that job easy. The voltage comes from whatever the battery source is, so 6 volts. Our 2 farads comes from reducing the circuit down. The result is to produce 12 coulombs of charge on the capacitor plates. Now, after you've done that, you're going to step backwards a step, applying to the previous circuit information that you have found from your current circuit. In this case, we know the charge on this capacitor has to be the same as the charge on all the capacitors that are in series. That's what we proved prior to this example. So there's 12 coulombs of charge on our equivalent capacitance. That means there must be 12 coulombs of charge here and 12 coulombs of charge here. So we've gone back a step, and we're applying the charge to our new circuit. With this information, we can figure out how the voltage is set up on these particular capacitors. We know that voltage equals charge divided by capacitance. So if I look at that top capacitor that has 12 coulombs of charge on it and 3 farads of capacitance, that must be 4 volts across that capacitor. Similarly, I have a 12 coulombs on the bottom capacitor, and it's a 6 farad capacitor. It's got to be 2 volts of potential difference across that capacitor. Now, at the end of the day, Kirchhoff's rules have to be satisfied. And it's a way to check your work, but I start with 6 volts, and I lose 4, that brings me down to 2 volts. I lose another 2, that brings me down to 0. The sum of the voltage drops in any loop has to equal 0. Now, there are ways to use Kirchhoff's laws to do this. In fact, we did use Kirchhoff's laws to do this. We used Kirchhoff's laws. We're just using that expression instead of using Kirchhoff's laws. Kirchhoff's laws make this a little more complicated because Kirchhoff's laws will generate some systems of equations that you then have to solve. Stepwise reduction is a means of using Kirchhoff's laws without using Kirchhoff's laws. I said to you, that entire book is filled with ways of using Kirchhoff's laws without having to actually use them. Stepwise reduction is one method to do so. Yes, sir?
If you can treat series capacitors like a single capacitor, then what's like the application for series capacitors?
What if I need a 2 farad capacitance, but I don't have one? But I have other capacitors that I could put in some arrangement.
Okay.
So
in like an ideal scenario.
your question is about, well, what's the point of doing this? Well, there's other things happening here too. Notice that I'm taking my 6 volt load and I'm splitting it in such a way that I have 4 volts across one capacitor and 2 volts across the other capacitor. What if I actually wasn't interested in a specific capacitance, but was interested in trying to find a way to get 4 volts from a 6 volt source? Well, I could do that too, right? From here to here, I could tap out on this side knowing that the voltage drop here is only 4 volts. So I could use this to divide the voltage up and then create a circuit off of that. Now that's oversimplifying it, because whatever I add here is likely to also then affect the total circuit. So I do need to maybe massage that a little bit and understand that that might affect the outcome, it might affect the voltage division. But when we're building circuits, one of the things we're trying to do is utilize the equipment we have. They don't make capacitors in every possible size. Also, something I'm leaving out of this, and that is that most capacitors are also limited as to the total amount of voltage that they can handle before they break down. Like the one we're going to use, says 5 volts. We'll actually be using a 6-volt source with it, but we'll be using it with a resistor when we actually do the lab with these, and it will ensure that we never get outside the range that this capacitor operates. You apply too much voltage to a capacitor, and the mysterious black smoke comes out. Don't breathe the black smoke. It's bad for you. But unless, of course, oh no, I don't want to say it out loud. I'll make some joke and somebody's feelings will be hurt. So let me just say it nicely. Don't breathe the black smoke. The mysterious black smoke generally is toxic. What's happened is you've applied too large a voltage to your capacitor and your capacitor failed. And failure generally means that there's a discharge between the plates. So you can force charges through a vacuum if you push hard enough. Somebody asked about that a while ago, I believe it was you. And so dielectrics make that even easier. And when you do that, generally the path of those charged particles ignites whatever your dielectric is. A lot of times these are suspended in oil as well to try and deal with heat and some other issues that happen in these circuits, and also they use sometimes oils as a dielectric. Once that stuff ignites and that smoke comes out, your capacitor's dead. Generally the two surfaces are now touching. So a couple of little things I want to point out here, since we're talking about solving circuits. The other thing that you should be equipped to solve for is the energy stored in each capacitor. It's kind of a final check here too. Energy is one of those things that we know there's a finite amount of, and it's conserved. If we look at the equivalent circuit, 1/2 CV squared, right? Total energy stored in that equivalent capacitance. 36, half of 36 is 18. 2 times 18 is 36 again, so 36 joules of energy. Right? Well, look at my original circuit. The top capacitor is 1/2 CV squared. And the bottom capacitor is 1/2 CV squared. 12 joules. 16 half 16 is 8. 3 times 8 is 24 joules. 24 joules plus 12 joules equals 36 joules. So your equivalent circuit behaves the same way as your actual circuit. The battery pumps out a specific amount of charge, and the same amount of energy has to be stored in both. The battery doesn't know what's connected to it. It just provides charge or current to meet the demand of what's connected. So we have done everything possible to solve this circuit. We know the voltage across all the circuit elements, we know the energy stored in all the capacitors. That's what solving a circuit is about. All right? There's more that we have to do. So let's go ahead and do that. If I draw on this like, this circuit is the same as that circuit. They might look like they're in parallel, but they're not. There's only one loop through this circuit. It takes up all of those circuit elements. You follow what I'm saying? So when you're given a thing, and I want to begin by saying we do need to deal with this circuit using Kirchhoff's laws to see if there's a rule here that we can use for stepwise reduction for parallel circuits. And this is a parallel circuit. I want you to understand that drawing the circuit using a circuit diagram, there's lots of different ways a circuit can be drawn that are equivalent. And sometimes the way in which a circuit is drawn is done purposely to be deceptive. These two circuits are the same. They represent the same thing. In fact, this circuit is also the same. All three of these represent the same circuit. Now remember, Kirchhoff's rules will tell you that, because Kirchhoff's rules will tell you the loops through the circuit, and therefore every one of these should have the same kind of loops through the circuit. Kirchhoff allows us to see that these are the same, but you have to be able to recognize that they represent the same thing, and that's sometimes not easy. So just like in the previous one, circuit diagram, pay a little attention, be careful, make sure you understand what it's saying. I'm going to operate on this one. This is the one I'm going to use for our discussion, but these are all identical. Before I do that, why don't you guys do me a quick favor, and assuming that our voltage supply is again V, generate your Kirchhoff's rule equation. Did you draw a loop through the circuit? Say this loop. That's a loop through the circuit. The problem is that loop only takes up one of the capacitors. If we want to make sure we're including what's happening to all the capacitors, we need a loop that encompasses all of the circuit elements. I'm not sure that can be done with one loop. It can probably be done with two, even though I think there's three possible loops here. Do you guys agree with that? Because, I mean, there's this loop. I mean, there's also this loop. I think there's three possible loops here. So there would be three possible Kirchhoff's equations, one for each loop. Now there's also a junction, but there's no current in the circuit. The charges instantaneously set themselves up here because there's no resistance. So technically, the wires probably have resistance, but we haven't introduced current yet, so we're just going to leave out the current equation and what's happening there and say that these voltages establish themselves instantaneously in the circuit, but which is actually not far off from the truth. So I want you to understand I'm not really lying to you. If the resistance is low enough, this will happen instantaneously. So, and there's a reasonable explanation as to why. But I think there are three loops, but we only need to have enough loops or enough equations to make sure we cover each circuit element. So although there are three, we only need two. Any two will do, as long as every circuit element is somehow taken into a loop. For example, I'm gonna write V minus VC1 equals 0. That's a potential Kirchhoff's loop. And also V minus VC2, that's also another possible loop. But there's also VC1 minus VC2 equals 0. Now, if you're asking why I didn't put a negative sign on both of those, that's because we're looking at the red loop. I know that that has to be the charge arrangement on that capacitor, and that has to be the charge arrangement on that capacitor, just from looking at the way it's connected to the voltage supply. So when I follow that red arrow around, I'm going from negative to positive, that's an increase in potential. And on the other side, I'm going from positive to negative, that's a decrease in potential. So I put the positive on the C1 because I'm increasing potential in that direction. All right? But ultimately, I think I'm going to use these two. They use the battery. And the thing I can guarantee is that the voltage from the battery is the same for both of these. Fair enough? Now again, we're trying to develop an idea for the equivalent capacitance. This one might be a little tougher to do. So I want you to realize that if C1 and C2 aren't the same, then my equivalent circuit is still going to look something like this. It has CT and the same power supply V. It's my equivalent circuit. V for capacitor 1 is going to look like V equals Q1 over C1. Is that good for you guys? And this one's going to be Q2 over C2. That also good for you guys? Just kind of solving, plugging in. Now, although V is the same in both of these, there's nothing to say that Q1 and Q2 would be the same. They'll be different. Right? Unlike the last one, these are separate. They're each kind of separately connected to the battery. So they're going to draw whatever amount of charges they need to charge up. On the other hand, my equivalent capacitance is also going to have a similar structure to it that we've seen already. Right? It's a single loop. So my equivalent capacitance is going to be V equals Q total over capacitance total. Now, hear me out. I think this is a reasonable idea. Wouldn't it be that the total charge the battery separates, wouldn't that have to be equal to the charge on the first capacitor and the charge on the second capacitor? Charge is a conserved quantity, so the number of charges, number of electrons that leave the battery on one side and enter the battery on the other is finite. So part of those go to capacitor 1 and part of those go to capacitor 2, but none are just left out. So whatever our equivalent capacitance is, it's got to be the sum of all the charges moved. Does that make reasonable sense to you? Because if so, then that means that Q1 equals VC1, Q2 equals VC2, and Q total equals VC total. Simple substitution is going to tell me that VC total equals VC1 plus VC2. Cancel out the V's, and C total equals C1 plus C2. This is the equation for capacitors in parallel. Obviously, any number of capacitors can be in parallel. We would just be adding them on, but it's just a simple sum. And again, we'll relate it back to this. Put more of them in parallel, you just get more surface area. Total capacitance increases. All right? Do I need to do a simple parallel example with numbers, or can we move on to something more interesting? I'll leave that to you. I'll let you decide. We can do a quick parallel one, or we can do what I'd really like you to see, which is some kind of system of capacitors. So let's do a simple system of capacitors problem. And by simple, I mean we'll just do a set of parallel and a set of series. All right, so I'm just trying to make a simple thing, simple numbers, just so you can see how this operates. So I have a system of capacitors now, more than just one set of parallel, one set of series. I have a combination. If you look at this, clearly there's several pathways through the circuit. We could look at setting up Kirchhoff's rules, and you can solve this using Kirchhoff's rules. It will create a system of equations. This one can create a system of 3 equations. And there's 3 equations and 3 unknowns. So you can figure out the charge and voltage across all the capacitors using Kirchhoff's rules. We're going to use stepwise reduction instead. It's not as efficient, but it's not any slower either. And it's just a little bit more time consuming on the drawing part. We're going to use stepwise reduction. And to use stepwise reduction, you reduce the circuit one step at a time. However, because there's multiple things here, you have to make sure you are very clear. You can only reduce things down that are parallel or series. And you can only do one at a time. Meaning, I know this 2 farad capacitor is eventually in series with this 3 farad capacitor, but it's trapped in a system where it's in parallel with the 4 farad capacitor. So although there is a series here, I have to reduce this down to 1 capacitance first, because it's a clear parallel element. So my first reduction, and this is what I generally do when I draw this out, is I try and reduce them one piece at a time, drawing out a piece of the circuit. I'm setting up a roadmap for how I'm going to reduce my circuit. I'm going to reduce the top into an equivalent circuit, just the top. I'm going to find a single capacitor that will replace that parallel series. That will leave me a set that will look like this. And this I am also going to reduce to a single capacitance. This is my stepwise reduction of my circuit. I'm doing it in steps. Now I have 2 that are in parallel, so to get the total capacitance, I merely add the 2 that are in parallel, giving me a 6 farad capacitance on the top. So that's my stepwise reduction. I now have 2 that are in series. We've done this one already, so I think I can skip the math part and say that this has got to be 2 farads. Now there's 12 volts here, which makes for 24 coulombs of charge. That's my final circuit, but I'm going to go back now and apply that here. I didn't get a chance to say something, so I hate to press on, but I need to. I'll put the 24 here and the 24 here. That makes this 24 divided by 6, 4 volts, and 24 divided by 3, 8 volts, for a total of 12 volts. You guys see what I'm doing? Now, this capacitor is this capacitor, so that's solved. However, when we go back here, we're not going to a series element, we're going to a parallel element. When you go back to a parallel element, you don't apply the charges. We don't know how the charges are distributed. You apply the voltage. These get 4 volts each because they're in parallel. Parallel capacitors have the same voltage. Series capacitors have the same charge. Everybody understand? So when you step back, you have to apply something different to series than you do to parallel.